need to remember when we're counting up operations, we need to remember what these for loops look like in actual code. Remember, they've got these three parts where we're initially assigning, or typically usually initializing a variable to a value, which is an assignment. Then we're evaluating a condition to determine whether or not we enter the block of the code block within the loop. And then at the end of each iteration, we're doing an increment, which is, I guess, an addition and an assignment. For our worksheet last day, we are only counting conditions. So a condition would be right here. This is one condition, and assignments. Oh. So let me move the chat over a little bit, actually. There we go. So again, we need to think about how often these three different parts of a for loop work. So in a for loop like this, again, what we know is we're doing the initial assignment just once. We're doing this just once. So we'd have, so if we were to kind of think about how this works, we'd have a single assignment to begin with. Then we know that every time this condition in the middle evaluates true, we're going to run the code in the for loop. So in this case, if I is going from 0 up to n, we're going to evaluate the condition n times. At the end of each of those n iterations, when that condition evaluates to true, we're also going to have our I++ at the end. And then eventually when I is incremented so its value is equal to n, we're going to break out of the loop. But that's going to be one final condition. So our general kind of for loop looked like something like that, where we've got the initial assignment, which happens 1. For each of the n iterations that we enter the loop, we've got a single condition and an assignment, and then we've got the final condition at the end. And then obviously there's other stuff that's going to happen inside of this loop n times as well. Any questions about the for loop stuff? Or how we're getting that general form in terms of the number of assignments, conditions, assignments and conditions for this? Yeah, no problem. So let's try and work through this example here and then jump to some recurrent stuff. So for our first line here, we know that this is just a single assignment. Then for the for loop, again, it's one of these things where we've got I going from 1 to n. So I guess this is similar to the for loop above, but instead of I starting at 0 and going less than n, it's saying start at 1 and go up to it, including n. So it's still going to be very similar to what we saw above, where we're going to have this one assignment to begin with. Then we're going to have n times the condition that we go evaluates to true, and all of the increments at the end of each of those iterations we go into the loop for. So the next thing we need to think about is the fact that in the little example I drew up at the top, we didn't actually have anything in the for loop. But now there's a whole bunch of things I'm going to do for all n times I have to kind of think about down here on the next line. So we know that what's going to happen is for each of the n iterations we go into this for loop, we're going to assign j to 1. So we're going to have that initial assignment there. Then we're also going to have to think about how many times this condition evaluates to true. So the condition of the inner loop. So let's just for now just say that we're going to do something x times. And what we're going to do in that x times is we're going to, for the x times we go into this inner for loop, we're going to have a condition to see if j is than or equal to I. And then at the end of that for loop, we're going to have that assignment where we increment our value of j. Oh, I guess, sorry. And inside this inner for loop, maybe I'll just do this all on the same line just because it might be a little bit easier. Inside the inner for loop, we've also got these two here. So we've got two assignments here that are also going to go inside this inner for loop that runs x times. Then at the very end, we've got our single condition to break us out of that inner for loop, which is again all part of this thing we're doing n times. Then we've got the final one condition to break us out of the outer for loop. So does it make sense where I'm getting all these values? Again, we've got our initial for loop, here, which happens, our initial for loop here that has a single assignment, and then it's got n condition plus assignments. Then inside the inner for loop, we've got a single assignment to set j equal to 1, and then we're going to loop through the inner for loop x times. We're going to have to think about what that x is later, but for each one of those, we're going to do the condition to go into the loop, the increment at the end, and then the two assignment operations within it. Then eventually we're going to have to break out of that loop for all n times that we enter the inner loop. And then at the very end, this is the final condition to break out of the outer loop. Make sense? So I guess now what we need to think about is how do we I guess first of all combine all these terms and also to think about what x is. So what I'll say is, why don't we down here we can kind of determine what x is. So how many times does x run? When I is 1, it's going to go from 1 to 1. Which is just ones. When I is 2, it's going to go from 1 to 2, which is twice. When I is 3, it's going to go 3 times. So I'm going to erase all this stuff. So if we think about the total number of times that this is going to run, it's going to go once, then twice, then 3 times, then 4 times, then 5 times, da, 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 da. So depending on what it's going to go, the number of times it's going to execute is going to be dependent on I. And we know that I up here is going to be 1, then it's going to be 2, then it's going to be 3, then it's going to be 4, all the way up to n. So this is eventually going to keep going like n minus 2 times plus n minus 1 times, all the way up to n times. So the final time when I is actually equal to n, our final outer for loop when it's equal to n, this inner for loop, the maximum number of times it'll ever run is n times. Does this still make sense? Okay, so now we need to think about all of these terms. So what we've actually got here is if we combine the first and the last term, if we add these two terms together, we've got 1 plus n, which is n plus 1. If we add the second term and the second last time, we've got n minus 1 plus 2, which is n plus 1. If we add the third term and the third last term, we've got all of these are equal to n plus 1. So again, n plus 1 equals n plus 1. Then we've got n minus 1 plus 2 equals n plus 1. We've got n minus 2 plus 3 equals n plus 1. So I'm just kind of combining all of these different terms as we count all the different these different n terms we're summing together. And what we're going to end up seeing that we've got n over 2 terms, or n over 2, I guess, not terms, I should say n over 2 summations here. Or I guess I could also say n over 2 pairs of n plus 1. So what this all evaluates to, or again, the number of times x is actually executed is actually going to be, we've got n over 2 pairs of n plus 1. So that is going to be what x is. So if we kind of go back and think about this, we've got, I'm going to now count up all these terms. So we've got, in green, I've got 3 operations that happen once. We've got 4 operations that happen n times. And then 4 operations that happen x times. So we've got, again, these 3 operations that happen once, plus n times 4 operations, plus x times also 4 operations, which is going to be 3 plus 4n plus, and then we've got this n over n plus 1 over 2 times 4. And we can kind of cancel these out. And what we'll get here is we'll have 3 plus 4n plus, I guess, n squared plus n over 2. Oh, sorry, there's a 2 there. Nope. Erase that. I thought I just canceled out the 2. So it's actually 2n squared plus 2n, which is going to give us at the end 2n squared. We're going to add our n terms plus 6n plus 3. Yeah, so this, I mean, yeah, so the sum of terms from 1 to n, that is a, yeah, that is, I guess, there is a, I just wasn't sure if this was something that you'd memorize at this point. So I just kind of showed, I drew out, again, I drew out this equation as opposed to saying that this is something that we can use. No, there shouldn't be an n times because I was just thinking about how many times is actually occurring. because again, we see that sometimes it is occurring n times, but it's not always, this x isn't always occurring n times. When in the first for loop, when I is 1, it's just happening once. So this, what I was drawing down here, Natalie, I can put it in green. What I was drawing down here was how many times that x was happening. And we were counting up the number of total times these 4 operations were executed. Yeah, they are. Any other questions about this? But I think this is as hard as you'll probably, I think about as hard as you'll see in the lab today, but there are some nested loops. So I wanted to make sure that we, and I think this is, some of the nested loops all just happen n times, whereas this does not, the inner loop does not always happen n times. It happens once, then twice, and 3 times, and 4 times. So it was a little bit more difficult to determine how many times these 4 operations that are involved with the inner loop actually occur. Any questions about this? Or can we move on to the recurrent stuff? So the recurrent stuff, we're going to be doing similar stuff with recurrence relations. So the main difference is that when we're counting operations, it's going to be, instead of using for loops, it's going to be using recursion. Okay. Yeah, so as I said, you will get more practice with this stuff in the lab, but and it'll start with kind of just the more simple stuff with a single loop, and then it'll move to some of these nested loop structures. So what I can jump to now is the recurrence relations PDF. So in the video I kind of walked through this factorial example where we called factorial with 5, and we saw that it's gonna, to solve factorial 5, we need to multiply 5 times whatever we get from factorial 4. But in order to get factorial 4, we need to know what factorial 3 is, et cetera, and we have to keep calling this function recursively, making these recursive calls until eventually that n is 1, and we can reach the base case, and we can return that value, and we can start kind of unwinding this recursion. So what I want to do first for this is, yeah, I got it open now. Okay. I should be able to write on this one. Nope, I can't write on this one. One sec. Okay, great. Okay, so the first thing we want to do for part A here is, given the recursive factorial algorithm, write the recurrence equation. So this isn't something we've seen before, but the recurrence equation is gonna be how we're going to start our runtime analysis, where we first need to think about what are the total number of operations. But what we're going to see here is that when we think about our runtime here, we've actually got 2 different cases. So we need to think about how many is there going to be when n is equal to 1, and how many is there going to be when n is 2 or greater. So when it's equal to 1, we've got this comparison and then a return. So when n is equal to 1, we can say it's just going to be 2. But when n is not equal to 1, we're still making this comparison when n is equal to 2. We're making this comparison, but then we're going down into the else. And so when n is 2 or greater, we're saying, is n less than or equal to 1? No. Okay. Well, then let's do this return, which is going to be, we're calling that kind of an assignment. And then we're also, the number of operations we're going to do is going to be based on this recursive call. So it's going to be the number of operations that occur in factorial of n minus 1. So what we're going to see here is that when n is greater than 2, it's going to be however many operations there are when we call this function with n being 1 less, plus the 2 operations that we did before that. So again, plus this condition checking if n is equal to 1 and the return. Yeah, 2 because 1 comparison, 1 assignment. Any questions about this? How is it 2? Because we've got a comparison and an assignment. We've got a return and an if. Which one are you not seeing, Agam? Okay, thanks. It is if n is less than or equal to 1. Oh, sorry. Yeah. Yeah, so if it's anything, I guess we've said that the integer is greater than or equal to 1. So that's why I had it there, because it can't be anything less than 1 by what we're saying the input to the function is. So that's why I put 1 here, because I know it's never going to be anything lower. But this could be less than or equal to 1. Any other questions? Okay, so I might actually have to zoom out here and then redraw this again really quick. Oh, it's not working. Okay. So given that we've got this this recurrence equation that is saying this is what the running time is, it's kind of based on n, whereas if it's ever greater than equal to 2, it's going to be t of n minus 1 plus 2, and then when we get to the base case, there's going to be 2 operations there. How do we get to t of n minus 1? Again, because if n is greater than 1, we're going to do this condition, which is 1 operation. We're going to then return, which is an operation. So there's 2 operations plus however many operations we do when we do this recursion. So again, we have to add all the operations that occur when we call this function recursively and do a whole bunch of other operations. So again, I'm going to start writing this out a little bit. So when we've got t of n equals t of n minus 1 plus 2, what we can do is if we kind of keep thinking about all these different cases, we can say, well, yes, if I want to know what t of n minus 1 is, I know that t of n minus 1 is equal to t of n minus 2 plus 2. And if I want to know what this is, I know that t of n minus 2 is equal to t of n minus 3 plus 2. And I can kind of keep doing this forever, all the way until I get to t of 2. I know that t of 2 is equal to t of 1 plus 2. And t of 1, we know from this first line up here, is finally going to be 2. So we know that I can whenever, if I've got an n, I can go all the way down, and then I can, kind of like what we did with recursion, in the video, and then I can say, okay, well, I can plug this number up to here, and then I can plug this number up to here. So I could, if I think about this, let me do it on the other side. I could say, well, I know that t of 1 is 1. So I know that t of 2 was t of 1 plus 2, which is going to be 2. Oh, sorry, t of 1 is 2. 2 plus 2, which is 4. I know that t of 3 is going to be 2 plus 2 plus 2. Oh. Because it's going to be the 4 above plus 2, which is 6. I know that, and again, I can say t of 4 is going to be 2 plus 2 plus 2 plus 2 equals 8. And what we might see here is that the number of 2's we're adding together is actually just the term here. So what we might see is if we kind of kept doing this all the way down to n, we'd see that it's just going to be n 2's. Yeah. Does this make sense? How we could again keep expanding this out forever and ever, and until we eventually, again, if our n was 8, we'd eventually kind of keep doing this down 8 times. Does this kind of make sense? So I'm going to show you one other form of doing this as well. Maybe I'll erase. I can just do it. I'll do it again over here. So another way of doing this is we've got t of n equals t of n minus 1 plus 2. And we can do this by, I guess, what I'm going to call repeated substitution. So I can then say, okay, well, then I know that t of n must also, I can replace this t of n minus 1 with what I've got here. Because I know over on the very left, I'm highlighting it in red. I actually can do it in a different color. Since we know over here that t of n minus 1 equals t of n minus 2 plus 2, I can replace this term with, I can substitute that term. So what we see here is that this is the same as replacing the t of n minus 1 with this t of n minus 2 plus 2. So I can say I can replace that with t of n minus 2 plus 2, and then I've still got the other plus 2 that was outside of it. I have to move our faces because it's going to overlap for me. Okay. And so I guess if I so this is also just t of n minus 2, I guess, plus 2 2's. But I can also replace that. I know I can replace, similarly to how I did my last replacement, I can actually replace this with this over here. And if I make that substitution, then I've got t of n minus 3 plus 2 plus the 2 2's, which is going to be t of n minus 3 plus, now I've got 3 2 terms. What I'm trying to do here is start thinking of a pattern. And what we might start seeing here, now after just kind of 2 sets of substitution, is if I was to kind of keep doing this, some k or I times. So if I was to do this I times, we'd see that I'm going to say that, again, we're always coming up with a t of n minus this number, whether it was 1, 2, 3, all the way up to I, plus I number of multiplying 2's together. And what I'll say now here is that our goal is to make a substitution here where this t term on the right hand side of our equation is eliminated. So we can replace this with a value we know. And a value we know is t of 1. We know that t of 1 is 2, which I'm circling on the right side. So I want to figure out how can I get this to be equal to just t of 1. So what I want is n minus I to be equal to 1. So if I solve for I here, we've got I equals n minus 1. And so if I let I be equal to n minus 1, what we'll see is this we'll shift this equation. So we don't have a recursive term here. We've got actual a value that we can evaluate. So if I just say I can let I equal n minus 1, what this is going to evaluate to is t of n minus 1. So I've just replaced the I there, plus n minus 1 2's. So again, solving this further, n minus n, or sorry, it was n minus n, this should be in parentheses. N minus 1, which is going to be n minus n, and this 1's going to go to a positive. So it's going to be t of 1 plus 2n minus 2. And now I know what t of 1 is. T of 1 we saw over in the orange on the bottom left is 2. So that's going to be 2 plus 2 of n minus 2. And if I collect those terms, we just know that t of n is just going to be 2n. So this is a way of just kind of solving it algebraically through substitution, as opposed to in the middle column here. So in the middle column, what we did is we kind of plugged in values starting at the base case, and it's called a bottom-up approach. We kind of went all the way to the bottom, where similar to how I did in the video, and plugged in the base case, and then plugged those values as we unwound it all the way back up, and until we saw a pattern. Whereas this other one is a top-down approach, where instead of actually going plugging in values in the base case, we can actually just solve this recurrence relation by substitution by eventually trying to remove the reference, the recursive reference on the right side, by plugging in a value that will replace that with a known value to get our final runtime. Yeah, I guess this is considered, this is just considered a bottom up. And this is a top down. Those are the two different approaches outlined in the textbook. I think so. So in general, I think for some of our more simple algorithms, this the bottom up approach is easy to kind of find a pattern here as we're doing this. Sometimes it's difficult to come up with that pattern. So doing this top down approach, when we're just substituting and writing it out, and then just finding a term to reduce this recursive tn minus whatever it is to the base case is sometimes easier than having to write out all these different terms from the base case up and look for a pattern. Any questions about this? Sorry, this was A up here. And this was all B. This whole thing down here was all B. But A was just writing the recurrence equation. B was solving it, and I just showed a bottom up or a top down approach. Any other questions? We've got about 10 minutes. What I'd like to do in our last 10 minutes is maybe do A and maybe one of the two approaches in question 2. So maybe we could get to A done and then the bottom up approach for question 2. And then unfortunately we might have to move the top down approach to tomorrow's lecture. Unless there are more questions. I can actually do a. So what I'll do is I'll actually launch a quick poll just to see how this first, how again, maybe if I gave a similar problem in terms of similar to factorial, where we had something where we had a base case, which was some number like 1 or 2 or 3, and then the other part was again t of n minus 1 plus a constant. If you could come up with part B, again, the bottom up or the top down approach, to be able to come up with a pattern to write the closed form of the runtime. How did I get this line right here? Is that, I got a private question right here. Is that what you're asking? I plugged in I equals n minus 1 to this right here. So I replaced I with n minus 1 and I replaced I with n minus 1. Because what we wanted to do was we wanted to figure out how to get it so our t term was the base case. We wanted this t term to go to 1. So I need to figure out what values to plug in there to get this, because then I can plug this, then I can just plug a number in here because I know what t of 1 is. Okay, so looking at the poll results, again, about a quarter of you are confident, 40% of you kind of think it makes sense, but we don't think we can answer it on our own. Again, we will get more practice with this. Some of you are neutral, and then again, 10% of you, it's still not quite making sense. So what we'll do is we'll take another look at this other side. So I'm going to have to, I can save this, I think, and then I'll clear it. So now what I want to do is do question 2 here. So I want to now we're evaluating this algorithm here. So what we're going to do to come up with our recurrence equation is we first want to start out by saying t of, actually I can just do it. I guess I can just do it here. Think about the base case when n is equal to 1. And what I'll say for this one, to keep this one simple, is what I'll say is that we're going to say that this is we're not even going to count this as an operation. We're to say a move operation when we're moving these pegs is not even going to be an operation. Does anyone know Are you familiar with this Towers of Hanoi problem? Yeah. So it's, yeah, when we've got, again, these three different pegs, and we've got disks on them that get smaller and smaller. We want to try to put all those disks in another thing, but we can never have a big disk on top of a disk that's smaller than it. I can send out a link. I can send out a link to the actual problem so you can play with it. There's probably a bunch of online simulators. I'll send out a link after lecture, but it's not actually super important to know how the game is played. We're just looking at a solution to this problem, because a recursive solution to the Towers of Hanoi is somewhat elegant compared to, it's something that a recursive solution is actually quite nice. But what we'll just say is, for the base case, all we're doing is we're making a single comparison. So all I'll say here is that, let's just say that there's one operation, and we're gonna skip the move, because we'll say that that's some other operation we're not counting. We're only going to count conditions and assignments when n is 1, and when n is greater than or equal to 2, we've still got that one single condition, because we're now going to go into the else part of it. So we're still going to make that condition. But then what I'll say here is we're actually going to have to figure out how many operations occur in both of these. We've got 2 recursive calls. So there's actually 2 recursive calls that we need to count up, plus the one that we got from the original if condition. Just to keep it simple now, because I guess it depends on how that move is implemented. I think it would probably just be a single assignment, but let's just skip it for now, just to try to get through this. Hopefully, try to get through the I guess bottom up approach for part B. Because adding extra constants here won't. The main thing I want to get you some exposure to is actually having it where there's actually 2 recursive calls, and that's what I really want to focus on for this second problem. So what we've got here is, now we can say T of n is 2 of we have to do 2 recursive calls, and we're making those recursive calls with n minus 1, plus we always have to do that if condition first. So again, if we wrote this, oh, that's bad. If we think about what this T of n minus 1 is, if we want to kind of think about what that's equal to, we know that T of n minus 1 is going to be 2. And we know that T of n minus 2 is going to be 2 T of n minus 3 plus 1. So similar to how I did it in the first problem, eventually we can go down and we know that T of 2 is going to be 2 of T1. I keep writing up extra parentheses there, sorry. Plus 1. And we know that T1 is going to just be a 1. So again, our bottom-up approach is just plugging in all these values all the way back up. So our bottom-up approach here is going to, we know that T of 1 is 1. We know that T of 2 is going to be equal to 2 times T of 1 plus 1 is going to be 3. We know that T of 3, what time do we got? Is 18. Is going to be 2 times T of 2, which is 2 times 3 plus 1, which is 7. We know that T4 is going to be 2 times T3 plus 1, 14, 15. And now we need to start thinking about a pattern here. I'll do one more term and then we can see if we can think of anything here. So does anyone see a pattern with these numbers 1, then 3, then 5, not 5, 1, then 3, then 7, then 15, then 31? So this was our 1 term, our 2 term, our 3 term, our 4 term, our 5 term. Yeah, they're all very similar to powers of 1 or powers of 2. So if we know, if we 2 to the power of, we think of our powers of 2, we've got that. So if we think about it, this first term is actually 2 to the power of that term minus 1. This is 2 to the power of 2 minus 1. This is 2 to the power of 3 minus 1. 2 to the, oh, not minus 3. 2 to the power of 3 minus 1. 2 to the power of 4 minus 1. 2 to the power of 5 minus 1. So yeah, this is actually, this 31 is actually 2 to the 5 minus 1. So it is, this term here is actually the power that we're multiplying by, that we're, the power that we're using for 2. So if I erase this really quickly, I know we've only got a minute left. What we'll see here is if we kept expanding this down, we'd eventually see that t of n is equal to 2 to the power of n minus 1. So as our n increases, the number of operations we're going to have to do is 2 to the power of that. And that's because there are, that might be what we expect if we look at the algorithm above. We've got these 2 different recursive calls. So as this gets bigger, the number of operations we're going to have to do is going to go up by multiplied by 2 every time. Because again, if n is 3, we're going to have to call n of 2 twice, and then for each of those n of 2s, we're going to have to call n of 1 twice for each of those n being 2. So again, this goes up exponentially. So the runtime of this recursive algorithm is a lot bigger than what we saw here when we just had in question 1, when we just were counting down from whatever n down to 1. This, we're making 2 calls for each one of these recursive calls. So these add up very very quickly. Let me just pull the chat over. Some of the monitor. Any questions about how we did this? So again, with the bottom-up approach, we're thinking about what the base case is, and then we're just, I guess on the left here, I kind of talked about how we can work our way down all the way to t of 1. We kind of just worked our way down to think about how we get to the base case. And then the bottom up, we just kind of started with that bottom one, that t of 1, and plugged that in. Then we went to the next term from the bottom up to t of 2. And we know that we've already got t of 1 done, so we can plug that in. Then we know that we've got t of 2 evaluated, so we can plug that in. We've got t of 3 evaluated, so we can plug that in. So it's just a lot of plugging things in and then thinking about, okay, can I come up with a pattern as I'm looking at the answers to here to come up with a general solution? Any questions before we call it? So we'll do the top down approach for this at the beginning of the day tomorrow, and you will get more practice with this in the labs. Not this week. This week is going to be more, I think, just focusing on loops, but you will get more practice in the future. Yeah, it looks like you're already doing the top down. Yeah, so we'll get there tomorrow. Yeah, I mean, you can choose on an assignment. I'll think about it. I will probably just ask for this closed form. But We'll see. I think for some of these ones so far, it looks like the bottom up might be the simplest, but I do think there will be some algorithms we'll see this term where we will need to know how to do it top down. So I guess it is kind of problem specific, and maybe on the assignment I can try to give you, maybe I will try to ask you to do one way and one another way, just to get some practice. Any other questions? All right, I'll stop.
The recording has stopped.